In this video tutorial, we will review some basic skills such as metric conversion, scientific notation, and how to read a graduated cylinder. Here in Canada and in most of the world, scientists typically use the metric system, also known as the Système International or SI units, when we measure things. In this course, we will focus on 3 units of measurement. They are the grams, liters, and meters. The grams, which has a symbol of a lowercase g, measures the mass of an object, or how heavy the object is. Meanwhile, liters, with a symbol of capital letter L, measures the volume of a substance, so how much space an object takes up. And finally, the one that you are probably most familiar with is meters, lowercase m is the symbol. It measures the length of an object. So anytime you see a number next to the symbol G, you know that they're referring to the grams, or how heavy an object is. In this case, it has a mass of 36 grams. If the symbol has changed to a capital letter L, you know that they're referring to the liters, right? So the volume, or how much space an object takes up. In this case, the object has a volume of 36 liters. And finally, if you see a lowercase m as a symbol, then you know that they're talking about the distance. In this case, it is a distance of 36 meters, or a length of 36 meters. And that's the beautiful thing about the metric system. One system is able to measure so many different characteristics or properties of a substance, such as its mass, volume, or length. All you have to do is put a prefix in the front, and suddenly you've got kilograms or milligrams. Change the units, and suddenly you have milliliters. Change the units again, and now we have kilometers, centimeters, or millimeters. I think many of you are familiar with the units of bytes, so kilobytes, megabytes, gigabytes of data. So like I said, it's a wonderful system. It measures so many different things. Now, for our course, we are going to focus on just these 6 prefixes: the kilo, the hecto, the deca, deci, centi, and milli. We can ignore the giga, the mega, and the micro for now. To help you remember the 6 prefixes and the order in which they come, I like to use the phrase King Henry died. How did he die? Drinking chocolate milk. So King is for kilo, Henry is for hecto, died is for deca. Now, of course, it's kind of spelled weird, but whatever. Now, the question mark, how did he die, refers to whatever base unit you are using. So if you're measuring mass, then use G. If you're measuring volume, use L. If you're measuring distance, use M. So whatever you're using the metric system for, use that symbol here. But only pick one symbol at a time. Next, we have drinking for deci, chocolate for centi, and milk for milli. Alright, so once again, King Henry died, spelt weird. How did he die? So what units are you using? Drinking chocolate milk. Alright, so let's practice by writing the correct abbreviation or symbol for each SI unit below. Here I see the gram, so I know I'll be using the symbol G, so I'm just going to write down the G. But then I see the prefix kilo, so I should write down the symbol K in front of it. And there it is. Kilogram has a symbol of kg. With the decaliter, I see that I'm switching to a new unit, the liter. So I'll write down the symbol capital letter L. Because the prefix deca is in the front, so I can put a DA here. And now I have the symbol DAL to represent the decaliter. In this next example, I see the word meter. So again, I've changed the units into a length measurement. So I'll write a lowercase m down. Then I see the prefix micro. So I'll write the symbol for micro below that, and I get micrometers. Now again, we won't be using the micro prefix in our course, but I wanted to put this example in just in case you ever encounter it so you know what it means. Alright, so what I want you to do at this point is to pause the video, try out the remaining questions, and then when you're done, unpause the video and we will take it up. And there we have it. The base unit is meter, M, gram, G, liter, L. Over here we have base unit meter, M, gram, G. In these three examples, we have a prefix of milli, so in green I've got another lowercase m. Centi, I've got a lowercase c, and milli, I've got a lowercase m again. Alright, now that we know how to write out the symbols, let's do some metric conversion. In this example, we want to convert 1,600 meters into kilometers. Since the base unit is meters, I'm going to change our question mark into meters as well because we are measuring distance. Now, in the metric system, when we're converting from one unit to another, all we're doing is just moving the decimal place. That's it. Since I'm moving from meters to kilometers, I'll be starting from here and going to the left. This requires me to jump once, twice, 3 times to the left, and that's just what I'll do with the actual decimal point itself. Now remember, if there's no decimal point in the number itself, you can assume that's always at the very end. So here we go. We're going to jump 3 to the left. 1, 2, 3. So the new location of my decimal is between the 1 and the 6, meaning 1,600 meters is equivalent to 1.6 kilometers. Now, make sure you're jumping in between numbers though. A common mistake I'll see students make is they'll jump on the actual number itself, 1, 2, 3, but decimals don't sit underneath the number. They have to be in between numbers. So when you're jumping, make sure you jump in between the numbers once, twice, and a third time so you know the exact location of where the decimal should be. Alright, so 1,600 meters is equivalent to 1.600 kilometers. Now, you could keep the extra zeros, or you can leave them off. Later on in future science courses, you'll learn about significant figures and when you should keep the zeros and when you should not keep the zeros. But for this course, put them in, don't put them in, not a big deal. So I will accept both 1.600 kilometers or 1.6 kilometers. Alright, let's try another example. Again, I'm going to write out my prefixes. King Henry died, spelt weird, of course. How did he die? Drinking chocolate milk. In question number 1, our base unit is the gram. So I'm going to replace the question mark with the gram. Now, I am going from the milligrams to the grams. So I'm moving from the prefix milligrams all the way to grams. This requires me to jump once, twice, 3 times to the left. So that's what I'm going to do. I don't see a decimal place here, so I can assume it's at the very end. We're going to jump once, twice, 3 times to the left, and that's where my decimal is going to be now. So I will accept that as 2.000 grams, or just leave it as 2 grams is also acceptable. Alright, so 2,000 milligrams is equivalent to 2 grams, and all you need is this lovely acronym at the top. Just count where you're going to. If you jump to the left, move the decimal to the left. If you're jumping to the right, move the decimal to the right. However many jumps are required here is the same number of jumps the decimal place will move as well. Let's try our next example. Since the base units are in liters, I will cross out the question mark and replace it with the liters. I'm now moving from liters to the milliliters, and that requires 1, 2, 3 jumps to the right. So let's do the same with the decimal point. 5, and since there's no decimals here written, I'm going to show it over here, and we're going to jump 3 to the right. 1, 2, 3, and that's where my new decimal place is going to be. Now I can't just leave empty spaces in between, so I must fill them out with zeros. So there it is. 5 liters is equivalent to 5,000 milliliters. Let me just write the decimal there. So 5000. Alright, let's try one more example. Here our base unit is the meters, so I'll cross out the question mark and replace it with meters, and we're going from centimeters to millimeters, so that would be from the C towards the M. That of course only requires 1 jump to the right, so that's what we'll do. 1, 6 decimals at the end, 1 jump to the right, so that's a new place for my decimal. Can't leave any blanks, so I'm going to put a 0 instead. And I can erase my rough work. Boop, boop, boop. Replace the X with a decimal if you want. And there's your answer. 16 centimeters is equivalent to 160 millimeters. Alright. So what I'm going to do is I'm going to let you sit there and give the rest of these a try. Pause the video at this point. Once you're done, unpause the video and we will take up the answers. And here are the answers. Our next topic is scientific notation. Quite often in science we deal with extremely large numbers and extremely small numbers. As an example, if you are taking grade 11 chemistry, we will be dealing with Avogadro's number quite often. Now imagine having to write this big number multiple times throughout a test. It would take up a lot of time, and you are likely to make a mistake by missing a zero or adding an extra zero by accident. To solve this problem, we like to use scientific notation. Now, I could write 100 as 10 times 10, or I can write 1000 as 10 times 10 times 10. I can also write 10,000 as 10 times 10 times 10 times 10. But all of this can be shortened by using exponents. So instead of writing out all these zeros, I can just use exponents to tell the reader how many zeros there are. 10 squared, 100. 10 cubed, 1000. 10 to the power of 4, 10,000. And that's how scientific notation works. By using exponents, I save myself the trouble of having to write out all these zeros. Let's look at this example. It's a very, very small number, and it's got a lot of zeros in between. And instead of writing all these zeros out, I can save myself time by using exponents. Now, scientific notation follows this format. We are trying to get rid of zeros, so we're going to ignore all these zeros at the beginning and look for the first number that is not a zero. And that would be a 5. So 5 is our first non-zero number. So I'll write that down. This is followed by the decimal. And there it is. Then we write out the rest of the number itself. In this case, it is a 2, 4, and a 1. Then we put in our exponents, times 10 to the power of. So this little symbol over here, in French they call it the accent circumflexe. We're just going to put a little house, I guess, this little arrow, shows that we are going to put an exponent there. Alright, so 10 to the power of. And now we count how many times we're going to move the decimal to its new location. So the decimal used to be here, but this is its new location between the 5 and the 2. So let's count how many jumps are required to get there. 1 jump, 2 jumps, 3 jumps, 4, 5, 6, and a 7th jump. So that means it's 10 to the power of 7. Once again, be careful. Make sure you're counting in between the numbers because that's where the decimal exists. Do not count jumps like this. 1, 2, 3, 4, because decimals don't exist underneath the number. No, no, no. Decimals must exist between numbers. So make sure you count in between the zeros themselves. Now, since this is a very tiny number, less than 1, we tell the reader that we're jumping to the right by putting a negative in front of the exponent. So remember, anytime you see a negative exponent, that means the number we're looking at is less than 1. If it's a positive exponent, that means the number is a big 1 and it's greater than 1. Alright, so 0.0000005241 in standard notation can be written as 5.241 times 10 to the power negative 7 in scientific notation. Now, just be aware, on a calculator, you would have to push the exponent button, this little accent circumflex. However, if you're writing this on a piece of paper, the symbol is not necessary. Just write the negative 7 above the 10. The accent circumflex symbol is only required when you're actually typing this into a calculator or typing this on a computer. Now, for the rest of these examples, I'm going to erase that symbol so we don't get confused any further, since I am just writing it out. Alright, let's try another example. So in example number 2, I'm going to search for the first non-zero number, so the first number that's not a 0, and the first number I encounter is the 5. So there's the number 5, and then I'm going to follow that with a decimal point, and then write out the rest of the number. In this case, it's the 0, 5. Now there's no need to put in this 0 over here because we're trying to get rid of zeros. So let's now tell the reader how many spaces they need to jump, times 10 to the power of. Since I don't see a decimal point anywhere here, I can assume it's at the very end, and I need the new decimal to be located over here, so that means I'm just going to jump to the left at this point. So 1 jump, 2 jumps, 3 jumps to get to the new location, so I can say 10 to the power of 3. Now, this is a big number. It's greater than 1, so I can leave it as a positive exponent. You don't put a negative exponent. The negative exponent is only when the number is small, less than 1, less than 1. But for anything large, we just leave it as a positive exponent so you can tell the reader which direction we are jumping in. Alright, so 5050 in standard notation is the same as writing out 5.05 times 10 to the power 3 in scientific notation. Now, some students do ask, well, if I'm trying to get rid of zeros, why did I include a 0 over here? Well, that 0 is a placeholder. It is very important. If you take away that 0, it changes the number itself. So for instance, if I had $505, I can't just take out this 0, because doing so would mean I only have $55, and that's a big difference. The zeros at the end, however, can be removed because they're factored into the exponent. It tells the reader that I am moving these decimal places, and as you know, if we move them, we fill in extra gaps with zeros anyway. So I'm allowed to get rid of the zeros at the very end, but don't get rid of the zeros in between the numbers because they will change the value itself. Let's try number 5, for example. The first non-zero number I find is a 1, so I'll put that there. Follow it up with a decimal, and then we write the rest of the number. But as you can see, there are no other numbers there except for zeros, which we're trying to get rid of, so I can leave it at that. Now, it's always weird having a decimal without any other numbers afterwards. I'm just going to erase it, otherwise someone might think it's a period to end a statement or end a sentence. And I'm just going to write down times 10 to the power of, well, the new location of the decimal is between the 1 and the 0, while the original location was at the very end, so let's count how many jumps. 1 jump, 2 jumps, 3 jumps, 4 jumps, 5 jumps, 6 jumps. So I'm going to write down 1 times 10 to the power 6. So as you can see, I can get rid of the zeros at the very end because they're already factored into the exponent. But I can't get rid of the zeros that are in between, otherwise they change the number themselves. Alright, so zeros at the very end, you can just ignore them, and they're factored into the exponent. But zeros that are in between numbers, they are placeholders. I gotta keep them in there. Alright, now since this one over here is a big number, it's greater than 1, I can leave that as a positive exponent, positive 6, to tell the reader that we're jumping to the left. Let's try number 3, and that'll be our last one here. Again, the first number that's not a 0 is an 8. Since there are no other numbers afterwards, I can just leave it at that. So now the new location of the decimal is here, and I can count how many jumps it takes to get there. 1, 2, 3, 4 jumps to get there, times 10 to the power of 4. Now again, since this is a small number, it's less than 1, I can just put a negative there for the exponent to tell the reader that now we are jumping to the right. So remember, anytime it's a very, very small number, less than 1, you must have a negative exponent to tell the reader which direction we are jumping in. Alright, so try these other examples. Press pause. When you're ready, press play, and you will have the answers at that point. Alright, and there's your answers. Moving ahead, let's try and do it in the opposite direction, converting from scientific notation into standard notations. That's just regular numbers, the ones that we are most familiar with. So in this case, I'm just going to rewrite the exact number I see over here, 1.5, and it says here times 10 to the power 3, so I got to make 3 jumps. But do I jump to the left or do I jump to the right? Because it's a positive exponent, I must jump to the right in order to make it a big number. So 3 jumps to the right gives me 1, 2, 3. Here's the new decimal point. Put in the zeros as your placeholders. Delete the old decimal, and you get 1500, which is a big number. Now, if you ever forget, should I jump to the right or should I jump to the left? Not a big deal. Just jump. So let's pretend I wasn't sure what to do. I'm going to jump to the left now. Jump to the left. 1, 2, 3. Here's the decimal. Fill it in with zeros, and then put a 0 in the front. And oh, look, this is 0.0015. Wait, delete the old decimal. That's a small number. It's not supposed to be a small number because the exponent says it's positive. So that tells me I jumped in the wrong direction. Jump right instead. Okay, so if it's a big number, positive exponent, you should be jumping right to make it a big number. If it's a negative exponent, gotta jump to the left in order to make it a small number. So once again, we jump to the right, 1, 2, 3, and now we've got a big number, which is what we want because it's a positive exponent. Let's try question number 3. Again, I'm just going to write down the number, 3.75. I see the exponent is 10 to the power negative 2, so it's going to be a smaller number. To make it a small number, I'm going to have to jump to the left. How many jumps to the left? 2 jumps to the left, so 1 and 2. Here's my new decimal place. Put a 0 as a placeholder and erase the old decimal, and we're good. However, to be good form or to have good habits, we don't like to just leave it like this. We prefer to put a 0 in the front. If you don't put a 0 in the front, sometimes a reader might mistake this as just a speck or a dot that was put in there. They might not know that it's a decimal. To ensure that the reader knows it's definitely decimal, you put a 0 in the front, and that leaves it as a more obvious number with very little chance of misinterpretation. My 0 kind of looks ugly. There we go. 0. So try and keep zeros in the front. Don't just leave it as a decimal by itself. That's not good form, not a good habit. You need to put a 0 in the front. Alright, so once again, we've got a negative exponent, and this is going to be a small number, less than 1 negative exponent. Alright, so I'm going to leave you to this over here. Press pause, and then press play once you're done to see what the answers are. Alright, and these are your answers. For our final topic, we will look at how to read the graduated cylinder. So this is the graduated cylinder. It's an instrument we use in the lab to measure the volume of liquid. Now, quite often the liquid has a tendency to stick to the sides of the graduated cylinder, and because it sticks to the side of the graduated cylinder, there's a little bit of a curvature in the liquid line itself. We call this curvature a meniscus. Now, the meniscus is quite exaggerated in this photo, or diagram rather. In reality, the curvature is not as obvious, but it is still there. Now, because of this meniscus, we have a problem. Do we measure the volume at point A, or do we measure the volume at point B? The answer is at point B, or rather the bottom of the meniscus. By reading the bottom of the meniscus, you are underestimating by just a small amount on either side. On the other hand, reading the top of the meniscus means you are overestimating the volume by quite a bit. So it's much better to underestimate by a small amount than to overestimate by a large amount, which is why we prefer to read the bottom of the meniscus. Now, on the graduated cylinder, you'll notice that only the long graduations, the long lines, the long markings have numbers on them. All the very short markings, the short graduations, do not have numbers on them. In order to determine what each of these markings represents, we have to do a quick little calculation. So here we go. So if this is the meniscus, we are going to take these two numbers above and below the meniscus and subtract them. So 15 minus 10 means 5, and that tells me the gap between here and here is worth 5 milliliters. I then count how many spaces are in between, 1, 2, 3, 4, 5, and divide it by this number, 5 spaces. This in turn tells me that each of these spaces is worth 1 milliliter. So if each space is worth 1 milliliter, that tells me the bottom of my meniscus reads a volume of 10, 11, 12, 13 milliliters. The volume on this graduated cylinder is 13 milliliters. Let's try another example. I see two numbers, 190, so I'm going to subtract them. This tells me that there is a gap of 10 milliliters between the 100 and the 90. And because there are 1, 2, 3, 4, 5 spaces between them, I can divide the 10 mils by the 5 spaces. I can tell that each space is worth 2 milliliters. So if this is 90, 92, 94, 96, 98 milliliters. So this graduated cylinder has a volume of 98 milliliters. Alright, so give these ones a try. Pause the video. When you're ready, press play and the answers will be revealed. And these are your answers.